Hello everyone, welcome to today's webinar, Ask the Experts about Fluid Flow Metrology. Today's webinar is sponsored by the UK Government's Department of Science, Innovation and Technology, also known as DSIT. We have received a lot of questions during the registration process and we're going to use these to begin. We will do our best to answer as many as we can, and if we run out of time, we will follow up afterwards. You can submit a question using the Q&A panel at the bottom right-hand side of your screen. Your questions will not be seen by any other attendees, and hopefully we'll have time to get to some of them. Finally, we are joining today from multiple locations, including our homes, so if you experience any technical glitches or hear any background noise, please bear with us. First of all, I would like to welcome Professor Manus Henry, Professor of Flow Measurement at Coventry University and the University of Oxford. Professor Henry is also the chair of the National Measurement Systems Flow Programme Expert Group, the PEG. I'm also joined by my two SUD colleagues. First of all, Dr. Chris Mills, an expert in Coriolis meters, who is active in many flow measurement technical committees and the development of several ISO metering standards. Dr. Gabriele Chinello, he is our CCUS lead and is also a technical advisor on CCUS metering to the UK Department of Energy Security and Net Zero, as well as participating in various ISO and BSI committees. I'm also joined by Dr. Piotr Traczykowski. Now, he is representing hydrogen fluid flow measurement, having been involved in hydrogen metrology for several years, in particular focusing on the hydrogen dispensed by hydrogen refueling stations. And finally, myself. I'm a principal consultant at TÜV National Engineering Laboratory. I've spent over 30 years working in the fluid flow metrology industry across many world areas. I also contribute to the development of ISO metering standards and BSI metering standards, and I'm currently focused on flare gas emissions quantification and technologies to reduce these emissions. Now, as a reminder, everyone, we are here to celebrate World Metrology Day, which was Monday. It's a celebration of the signature of the Meter Convention, which took place in 1875 and was signed by 17 nations. The convention set the framework for global collaboration in the science of measurement and its industrial, commercial, and societal applications. The original aim of the Meter Convention, the worldwide uniformity of measurement, remains as important today as it was in 1875. Okay, I'm going to bring up the first question. This was sent in by Richard. I won't say any more for GDPR reasons. This question ties in very well with the theme of this year's World Metrology Day, which is we measure today for a sustainable tomorrow. So the question, which I'll read out, although it's on your screen, is this. The energy transition requires metrology to move its focus from fossil-based fuels such as oil and natural gas to a host of new fuels including ethanol, hydrogen, methanol, ammonia, biofuels, as well as CO2 for CCUS. With many of these requiring measurement in multiple phases, including the supercritical phase, accurate measurement will be key to enabling stakeholders to meet their net zero goals. Does the panel think that metrology in general is responding to this growing need, and if not, what is required to achieve it? Now, for this first question, can I perhaps go to Chris first?
Yep. Hello, everyone. Thanks, Colin. I think we can say the answer to this question is yes, and then just move on to the next question.
Thank you, Chris.
It's a good question, and I'm fortunate at NEL that I get to be involved in various UK level research projects, but also European led research projects as part of NPR, and I can confidently state that there's a lot of research going on both at a UK level and also a European level for the energy transition. So areas such as hydrogen, domestic use, so domestic gas meters, hydrogen refueling station. We're doing a lot of work there as well for hydrogen vehicles. Also just the measurement, the flow measurement of hydrogen for maybe industry as well in the future. And also CO2. We're heavily involved in CCUS, certainly at NEL, both in the UK and also with regards to European level research. And the research is crucial. So this research is both project research looking at flow measurement, performance of flow meters, etc., and how they maybe perform in these new fluids or these challenging fluids. But it's also about developing standards, regulations and facilities that helps underpin this research. So again, we're fortunate here at NEL. We are currently developing several new facilities as part of the energy transition. I'm currently involved in the development of a liquid CO2 facility. It'll be one of the first traceable liquid CO2 facilities in the world. We also have a gas CO2 facility, and we have other facilities for hydrogen just now as well. We're doing a lot of domestic gas metering research. That's with respect to domestic gas meters operating either with a blend of natural gas and hydrogen, or pure hydrogen, as the case may be in the future. And we've also been involved with hydrogen refueling station standards as well. So I think there is a lot of investment. There's a lot of research ongoing. And I also know that a lot of the manufacturers are heavily involved in this research as well. They're keen to develop their flow meters so that they can apply them to these fluids, be it hydrogen, ammonia, biofuels, or carbon dioxide. So yes, I would say there's a lot of work ongoing just now. As part of our remit as well, we are developing best practice guides. As you mentioned earlier, Colin, we're heavily involved in standards as well. And a key part of our remit will be influencing standards to make them relevant as they go forward for the energy transition, so that they're applicable to hydrogen measurement, for example. So yes, I would say so, and maybe I'm keen to hear the thoughts of anyone else on the panel.
Just before I come to Gabriele and Piotr, one of the attendees has messaged in to say that the stream is breaking up quite badly. I hope that is not the case for everyone. If it is the case for everyone, I can only apologise. We've done our very best to make sure it didn't happen. So if it is suboptimal, I can only apologise. Gabriele, you had something you wanted to add?
Yes, can you hear me? Right, yeah. Yes. As Chris said, there are a lot of projects, and that's definitely one of the focus of the metrology community now is, moving to these new renewable, let's say, more sustainable fuels, and also to digitalization. But when I go back to the question, when we mention ethanol, hydrogen, methanol, ammonia, biofuel, and CO2, this fluid have been measured for years. Probably not at the scale that we are looking now, and probably not at the accuracy level that we are now looking for. But what I'm trying to say is, to my understanding, the fundamental nature of flow measurement is not in doubt. And the technology out there, is, in a certain sense, fundamentally fit for purpose. What probably we need to look in terms of technology is maybe to have a bit more attention of material selection. Maybe some technologies need to change transducer. I'm thinking about USM, or modifying the tuning Peter or so on. But I think fundamentally the principles are the same. What instead I think we need really is knowledge. We need to gather the knowledge which ultimately underpin the measurement and ultimately underpin certification and validation of the meters. That's, I think, what we need to get up to speed now, is to get the body of knowledge that is required to ultimately trust the measurement and certify the instrumentation for these fluids. And in that sense, I go to what I think is one of the critical points, in my view, at least. To gather knowledge, we need test facilities, and we need to conduct the research. That takes time and takes resources. So I think that, to me, at the moment, for certain fluid is the point that we probably need to really focus on, especially when I look at large scale facilities. When we are looking at the size that the industry needs for certain fluid, we are lacking traceable large scale facilities. And it is a bit of a, I think overall in the world we are a bit stuck, because from a commercial point of view, an investment of such large facility is not yet justified. There are not yet all this infrastructure for CO2, all this infrastructure for hydrogen. We are talking about them. There are a lot of projects. But in terms of number of meters to be calibrated annually, there's probably a lack in justification for a big facilities. And that, it's a bit of a constraint, because if we don't have the facility, we cannot do the research. So I think that's where we are stuck at the minute. And unless there is some early mover or some of government involvement or some of the big companies' involvement that push through these, we will need to operate with more small-scale facility, which is what we are doing. We are operating, we are doing our best. And also in the UK, the government is supporting us immensely. Vast majority of what we do is from the Department for Science, Innovation and Technology. So at least in the UK, there is this push, and it needs to be recognized. And I will shut up now and pass to Piotr. I think he was looking to speak as well on this point.
Yes, so my view is more focused and more from the point of hydrogen. So basically what we use, we measure the flow. So flow meters, in principle, the same technology can be used with hydrogen as you can use with other fluids, but the degree of modification needed, it's sometimes different between the meter types. So the simplest one, let's say mechanical orifice plate, it can be used straightforwardly with hydrogen. The only requirement is that your pressure, temperature sensors needs to be compliant with the ATEX group 2C gases, so the explosives ones. So hydrogen is the most explosive gas we know. But then for the discharge coefficient, the hydrogen, it should be just as another gas, meaning that the hydrogen calibration straight isn't really needed. So then you can calibrate your sensors in other gas. We are quite confident about this, but we need just more evidence to prove it. And that builds the problem, as Gabriele pointed, that we need the facilities, sometimes big ones. On the other hand, the scale, we know that, for example, the commercial ultrasonic meters that are often used for households, they are designed for use with natural gas. They don't often work straightforward with hydrogen because the differences in the acoustic properties, the principle of operating of the ultrasonic meter, it's just different. But the manufacturers are already developing and testing the hydrogen ready versions, so the ones that will somehow handle this problem. There are some gaps in the technology. I would say that meter manufacturers are trying, to hold things back. Then the other example is the standards. We often have standards related straight to existing fluids. So some committees are struggling because there is a lack of evidence to base the decisions on. So again, experimental work is required. We just need more test facilities and just more data. Then there's just lack of traceable calibration facilities, especially for the big meters like DN50. This is the engineering problem because no one wants to build a large facility with most dangerous gas you can basically have. It's not just that engineering problem;
Yeah.
it's also ATEX related issues, regulations, pressure, all of this. So that's how it works. We, for example, did that in NEL. We built the facility for testing hydrogen refueling stations, and although the facility itself is quite simple, the amount of problems we had to solve on the way to make it running was enormous. So
Okay.
imagine that you have like a stationary facility with huge amount of hydrogen.
Okay. You seem to be breaking up for me a little, Piotr. Again, I apologise to everyone on the call. Manus, did you have anything you'd like to add in that question? I noticed Gabriele maybe had something, or perhaps it's 20 past, perhaps you could move on to another question. Anything to say, Manus?
Well, just briefly, I would agree with what the other guys have said about that. There's an awful lot of work going on, and we all have been involved in various ways in addressing the challenges of these new fluids. One of the issues for, say, CO2 is that very often it's going to be multi-phase, as mentioned in the question, and that raises particular challenges for many of the different metering technologies. But it's just worth commenting on government policy. About a year ago, I wrote a piece for the Institute of Measurement and Control out on this area, and as part of that, I looked at the UK government's net zero strategy. And what was fascinating was that whenever the document used the term flow, it was always talking about financial flows, right? And about the need to direct large-scale financial resources towards the green economy. And it mentioned only two exceptions to that. One, it mentioned actually what we recognise as flow, so development of data systems to connect energy, waste and water flows from industrial sites. That was one. And then the other was about the flow of innovation, talking about the need for, where is it now? Innovation does not flow neatly in one direction from one phase to the next. It is unpredictable and serendipitous, involving constant cycles of learning, testing, refining, and discovery. All true and very romantic language being used. At the same time, Tony Blair, in an interview at the time, said something about the number one issue today is how do you finance the energy transition and how do you accelerate the technology? And so you've got this sort of parallel worlds and parallel streams. You've got the financial economy on the one hand, and what we deal with is the physical material economy, the flow of all these materials going through the economy, and the need to meter those and the challenges of doing that. So with what the other guys have all mentioned, the need for flow facilities, large-scale flow facilities, for us to do the research, to demonstrate whether we need new instruments or verify that the current instruments work for these particular flows, that the resources needed to do this are a drop in the ocean compared to what is envisaged on the larger scale for the green economy. And yet we do need that. And yes, the DTI, DCIT is putting money through the flow program into resourcing this, but we need much larger facilities in order to deliver, particularly on this ambitious timescale that is being asked of us. And just one, I think one final point that's probably worth mentioning is also the need for policy stability, because I think we've all seen, switches in emphasis between, say, hydrogen and CO2 and this scheme and then that scheme and so on. And given the timescale that is being demanded for net zero and the energy transition, I think we need stability in UK government policy and realistic deadlines for technology development and rollout, and that includes providing the facilities to help everyone to develop and test and verify and standardise what we need to do with these instruments.
Okay, thank you, Manus. I think, I know you had your hand up, Gabriele, but there's actually questions coming in, and we have some pre-registered questions. So if you don't mind, everyone, I'm just going to bring up the next question again. It's quite a wordy question, but you know we'd expect that from an educated audience. And it seems to be, you know, it's a subject that's coming up quite a lot. So the question is, the time-based calibration of measuring instruments based on the SI units traceability pyramid, international standards and national measurement institutes has served the science of metrology exceptionally well for decades, even centuries. Advances in instrument diagnostic capabilities and data sciences, such as machine learning, are seeing a push towards the use of condition-based calibration to primarily reduce operating costs. Does the panel think that there is a danger of moving too far from the established and proven time-based traceable calibration methodology? And if they do, what are the dangers and how can they be addressed? Can I maybe suggest, Manus, do you have any thoughts on that primarily?
Oh, yes. This question allows me to get onto one of my sort of old hobby horses, which is the concept of the self-validating or the sievert sensor, which addresses this whole area. Okay, so this was something my professor David Clark back in the day and I worked. This was in the 1990s, and this ultimately resulted in a British standard BS 7986, which came out first of all in 2001. It was revised in 2005, but it's not been widely adopted. It's not been used at all. And the key idea is to integrate diagnostics and metrology, so that instead of a device generating some device-specific error code or the equivalent, what a sievert sensor is required to do is to generate online and dynamic uncertainty estimates, okay, which take into account whatever's going on, so that the time since the last calibration, the operating points, the diagnostic reasoning that may be specific to the device. But all of that gets combined into providing an online uncertainty estimate, which then ties in with the whole metrology scheme that has been established for centuries, well, for a while, shall we say. And there's several advantages to this. First of all, any system, any plant control system, whatever, can decide on how valuable that measurement is, whether to carry on using it or to substitute or do whatever else, based on that quality, its uncertainty, without having to interpret any device-specific error codes or whatever from the device. But it also retains this importance of traceability, because vendors offering diagnostics will be required to map those diagnostics of the detected conditions into a corresponding increased uncertainty, so which can then be externally verified in NMI labs. Okay, so that it might be in the end that individual instruments are calibrated less often and possibly on the basis of condition-based monitoring, but the calibration procedure itself, and especially the initial certification of some new product, will have to be more varied and sophisticated, because it will need to verify the diagnostic performance and indeed the metrological performance, as well as conventional fault-free performance. And that will retain, which is really important, is to retain the sort of primacy of the metrology lab. Okay, and so an example of this is you know, I'm a Coriolis guy. You know, we developed this idea working with Coriolis and gas and liquid mixtures. And again, back in the 90s, a Coriolis meter would simply shut down with entrained gas. Okay, so it just shut down. And then with the development of digital drive, you could maintain operation, but the flow and density measurements would have large systematic errors. And then we could develop corrections for that. But even so, the residual uncertainty of a two-phase flow measurement in Coriolis is at least 10 times greater than that for a pure fluid. So ideally, the meter should be able to generate online uncertainty estimates to indicate the probable error on your measurement, which will vary dynamically as the current operating point and all the rest of it. And that then feeds into the high-level control and accounting systems. Okay, so overall, this kind of scheme would preserve the sort of the primacy or the supremacy of metrology itself and the authority of the NMI labs, which is essential to keep. Okay, because otherwise we're at risk of getting lost in a whole mass of vendor-owned, vendor-specific diagnostic, device-specific diagnostics, and which may, under market pressures, lead to excessive time between instrument calibrations. Okay, it's very easy to just remove the authority of the NMI labs and the primacy of traceability. So I think the key attraction of the SEVA scheme is to develop diagnostics, device-specific, which the vendors can innovate and patent and all the rest of it, but tie that into the existing metrology scheme through dynamic online uncertainty.
Manus, what a fantastic answer. I very much doubt if any of your co-panelists can actually elaborate on that, but I will give them the opportunity if they want. Chris?
Yeah, it was maybe not so much elaborating on it, because it was a great point by Manus. Maybe looking at the question around diagnostics in a different way. So I've been involved in flow now for 16 years, over 16 years, so quite a long time. When I first started, there was a lot of mention of diagnostics. There was a few papers, one of which you co-authored, Colin, around ultrasonic diagnostics, and people extending their calibration intervals. Now, without sounding too much like a Luddite here, I would say that diagnostics are readily available, and they have been, and Manus is fully aware of them as well for Coriolis meters and other technologies. And I think there still is a real barrier to people actually using diagnostics. I still don't think a lot of people are using them. They may have them, so they may have the flow meters with advanced diagnostics available, maybe more so for maintenance-based issues, flagging up as an issue with a transducer, for example. And personally, I don't think enough people are using them, whether that's because there's an issue with knowledge, or whether, as Manus says, there's so many different vendors, each with their own specific terms for diagnostics, for diagnostic parameters, and different bits of software, that it's almost impossible to be fully aware of them all, and to be knowledgeable of them all. And I also think there's an issue around folk are comfortable with what they're currently doing. So there's always the adage of, well, that's what we've always done. So people send their meter off for recalibration on a calendar-based approach, so once a year, for example, back to NEL or another calibration laboratory, and they're comfortable with it. They get that certificate, and it's an easy approach for them. Changing to diagnostics is a challenge. There's a skill. You have to pick up knowledge to learn how to fully apply the diagnostics, and as touched upon, what do the diagnostics tell you? Do they apply an uncertainty? Do they flag up as an issue? I also think there's a secondary issue. I like to think about it like cars. Cars have diagnostics, or modern cars have diagnostics, and they're fairly advanced now. But what are they telling you? They're telling you about maintenance. They tell you about your service requirements. Whereas I like to think of the calibration almost being like your MOT, so your test that has to be completed yearly, and that's still in a calendar-based approach, and there's no discussion ever moving that to a diagnostic-based approach. That's your calibration, and that's still checked yearly. Now, you can have maintenance, where you might want to check if transducers are okay, if the flow conditioner is blocked, for example, and that could be your maintenance, like a service for your car. It's now, for a lot of modern cars, it isn't calendar-based approach, it's diagnostic-based approach. So I think there's almost two steps to it for diagnostics. There's one around the maintenance and kind of help you reduce your maintenance and ideally tell you if there's an issue. But I still think there's a time and a place, going back to that question, for a calendar-based approach to calibrations. I still think that's, in the near future, certainly, that's still going to be a key part. I can't see it changing in the near term, partly due to people being comfortable with what they're doing. And I know a lot of our customers and other people still stick to a calendar-based approach rather than a risk-based approach for calibration. Also because it provides them with confidence. If you move to a diagnostic-based approach, and it might extend your interval, let's say, to 7 months, just a random month. What if you then discover there's an issue at that point when you recalibrate it? You've then been operating for 27 months between calibrations. When did the meter shift? And you could have a large financial risk because of that. So there's various things to consider, I think, around that question. We'd be interested to hear what other folks think. And I'm a really just a Luddite stuck in the past.
No, Chris, another fantastic contribution. Thank you. And I think, you've hit the nail on the head. I mean, the comfort that people get and the confidence they get from a traceable calibration, especially when we're talking about, financial risks that are running into the millions, tens of millions of euros or dollars or pounds. It's kind of hard, to fully give your faith to diagnostic data if you stand to lose, or be sued for numbers with lots and lots of zeros at the end. Gabriele, Piotr, anything you want to add to that, or should I move to the next question?
Just maybe I've had to agree with Chris, because what we observe, for example, on the hydrogen refueling stations, the Coriolis flow meter is like the core of the measurement. It's often being installed there, and then the maintenance ends. Sometimes the staff there has is not being aware of that. They have to check the zero, for example. Does it drift? Is it drifted? Did it change something? No, they just keep it there in the line, and sending for calibrations is the last thing they think about, because if they send that meter for calibration, that means the station needs to be shut down, right? And they are not aware, what the error is being carried by this flow meter, and there is no scheduled plan. We send it every year, for example, for just calibration, even in hydrogen, even in nitrogen, that will tell you, it drifted, it changed. Do something about that, yeah, because there's no facility to calibrate it in hydrogen. We have such facility. Maybe I'll talk about this later, but it tests the whole refueling station, not just this flow meter. So if there are leaks or any other contributions, well, that's all included in the total error that we can discover. We can help with diagnostics. We can, of course, that's our also the purpose of our facility. But the operator needs to be aware. Okay, I got this flow meter or any other sensors. There are temperature sensors, pressure sensors. It's to my understanding, some of the operators just keep it as is, and they don't bother until it breaks.
Yeah, that's right. There's actually a question about, which is maybe relevant to that later. If you don't mind, folks, I'm the moderator. I'm conscious of time, so I'm going to put on to the next question. And again, this has been very interesting to me. The questions that are coming in, we have some about meter types, but a lot of them are on the same theme of modern digital development. So this question here, with the latest developments in AI, machine learning, and CBM, how will they influence the development and adoption of certain flow measurement systems? For example, is there still going to be a place for the humble orifice plate, PD meter and turbine meter, etc. in the future? And how might these traditional methods evolve to remain relevant in modern applications? Again, I'm going in the order of faces on the screen here, so I'm going to pick on you again, Chris. Do you have any comments on that?
No, just to apologise that it's my face that you see first. Go on. That's an excellent question. And as you say, almost partly touched upon the previous question around AI and CBM and diagnostics. And although maybe I was a bit negative on them in the previous response, they definitely do have a large part to play with the design of metering systems. And I think going forward, well, it's certainly something we've noticed, even just for calibrating meters here at NEL, that, again, going back to when I first started NEL, a lot of the meters we've seen were PD meters, turbine meters, but over the past 15, 16 years, it really has moved really towards Coriolis meters predominantly, and also ultrasonic meters that offer these diagnostics. So people do want diagnostics, and they certainly are going to influence design going forward. What does AI and machine learning do to that? Well, we're obviously just at the start of the AI revolution, maybe as it likes to be known as. I can't quite predict how that's going to go in the future. I don't think anyone can. I'm sure there's going to be a lot of development. Maybe what I personally like to see, so we have the diagnostics just now, and maybe they're more qualitative rather than the quantitative diagnostics that we really want to get. But I also think maybe AI can help, a bit like ChatGPT. It can actually correspond with the end user, almost like a sci-fi film, maybe, and it will tell them there's an issue and actually tell them how to go about diagnosing it. And you can almost have a conversation with them to say, I've already tried steps X, Y, Z, and then they can recommend you could try other steps to overcome maybe the issues or to send it away for calibration, for example. So maybe that's the next development with AI around diagnostics for these flow meters and how we use them. I don't know, I'm just theorising just now. But looks like the question's almost twofold. So the second part of the question is around maybe more traditional meter types. And yes, there's definitely still a place for them. So obviously we're the designated institute for flow here in the UK. And when we're designing our own metering systems, be it our secondary reference system to our primary, the flow meters that we often select are traditional flow meters. So we'd maybe pick a turbine meter or a PD meter or a differential pressure device for a comparison, because we have confidence in their performance. We know they're stable, they're repeatable, reproducible. There's a lot of history, a lot of confidence in these devices. And I'll let other folks talk in a second because I realise I'm going on a bit. But I also am fortunate to represent NEL on a European and world level for key comparisons with other NMIs and DIs around the world. And when you perform comparisons, you pick a transfer standard, and that's a flow meter that you have confidence in. And 99% of the devices that are picked for these comparisons are traditional flow meters, be it a differential pressure device like an orifice plate, a Venturi, or be it a turbine or a PD meter. Because people have confidence in them and send them to another laboratory and have confidence that they're going to perform well and that they will perform close to the historic performance. So I hope that maybe partly answers it, and I'll let some other folk talk now.
No, thank you very much for that, Chris. Again, a comprehensive answer. I didn't actually see any hands go up during there, but is there anyone wants to Gabriele? Please go ahead.
Yes, let me defend the humble orifice plate. Yes, the humble orifice plate, as far as I know, is still one of the most popular installed meter out there, at least legacy meter in some cases, but I've read about some figure of 40% of installed meters are DP meter, differential pressure meters. So we still need to deal with them. Second point, there has been a lot of advance for the orifice meter, for example, or Venturi diagnostic anyway. So now we can use the differential pressure signal in a very nice and elegant way, and there are diagnostic software out there already on the market since years. So that's an example of something that had followed the trend and has adapted, and there are commercial software out there that use the signal from differential pressure transmitters to actually offer a lot of diagnostic information. Regarding AI, machine learning, condition-based monitoring, I just go back to what Manus said, and I think that's probably the key point. There are a lot of development. Flow meters can offer a lot, but I think the key question is always traceability and validation and certification. We can use and standardization at the end. We can use this method, but we still need someone that tell us that these methods are reliable, and we have a piece of paper that says this is good to go. So also, if we use whatever nice machine learning we can do, we still need to certify this machine learning, and we need someone that rubber stamp this method. So if we go down that road, and I think that's what is going to happen in the future, the traceability certification, quality assurance, standards are still required anyway. So that's actually my thinking. And I'll pass over to Manus or to Piotr.
Oh, Piotr. Go ahead, Piotr,
Thank you.
please.
I just wanted to ask. Sorry, that's the lag, unfortunately. Yeah, so I just wanted to add a few words that I'm actually a great fan of simple devices. So we recently even did like an intercomparison or just a comparison, and the device used was just a sonic nozzle, the most simple that you can use. The secondary standard was the Coriolis meter, and of course, yeah, the Coriolis meter is very convenient, but sometimes you don't want to spend money for the Coriolis meter, and the sonic nozzle might be just cheap enough and cover your requirements. It's just a matter of your purpose and your, how much money you want to spend. It's also easy of use. The Coriolis meter requires maybe more electricity. Why the sonic nozzle, for example, is just a mechanical device, pressure sensor, temperature sensors, and that's all you have. Of course, it requires occasional calibration as well as any other device, but still it provides necessary data. Can be used, for example, as another standard on the line. Like I mentioned, for example, refueling station can replace or just have like a parallel line using, for example, sonic nozzle when they send a flow meter for calibration. That's just one of the options. So it's not that it's gonna die out, that the simple devices will just vanish because we have more modern approach. They will still be in use. It's just a matter of costs and your application.
Manus?
Just quickly, I'm in a sense even more cynical because, look, all flow measurement techniques require some form of transduction, first of all. So some form of mechanical interaction, even if you're just attaching a clamp or an ultrasonic meter to the outside of a pipe. So the sort of mechanical and broadly analog elements of a flow meter can never be completely eliminated, right? And in fact, I think that it's possible that these low-cost, purely mechanical technologies may get a new lease of life when combined with more sophisticated software to compensate for their limitations. Okay, you don't get the sort of richness of signals as you get from a Coriolis, but maybe if AI is clever enough, that's enough, as it were. And also with the energy transition and so on, and with so many new flow meters needed, this might be exactly the solution that's actually required, rather than, as you say, the more expensive Coriolis and so on. And of course, there's the issue of maintenance and downtime and so on. So the ultrasonic and the Coriolis may need less of that. But I suppose here's the real point. From a top-down AI machine learning perspective, it doesn't particularly matter what the underlying transducer technology is anyway, right? So as an editor of a flow journal, I'm seeing dozens of papers on applying machine learning techniques to flow measurement, and there's a pretty uniform way in which they tackle flow measurement problems, irrespective of the underlying technology. Okay, so I think the real risk, and what perhaps underlies the question really, is the loss of flow measurement culture or practice, or the engineering experience and understanding that goes alongside the use of these particular metering techniques, okay? And there is a potential risk that in the end, practically no one bothers to learn the details of how these technologies have been used. Maybe we'll have robots that manufacture the things and install the things, and we just trust that some AI module will interpret the data appropriately, okay? So that it's all fine until it all goes horribly wrong, right? So I think really the question is more about the flow metering culture, as it were, and the knowledge and understanding and craft of the business, of whether that will get lost in the AI, and how we balance maintaining the fundamental skills and judgment that's needed to maintain the craft, while of course offloading the boring stuff onto the AI systems where that can be safely done.
Thanks, Manus. We only have about 5 minutes left because I have a few closing statements to make. I'm going to take one of the questions that's come in from one of the audience, because I think it's unlike the previous questions, more of a yes or no question. Now, I don't want to put you guys in the spot because you haven't seen this question before, so I need you to pay attention. The question is, will fluids at pressures well above critical pressure have homogeneous density and phase as they transition above and below the critical temperature?
Sorry again, Colin, I missed the first part.
Sure. Will fluids at pressures well above critical pressure have homogeneous density and phase as they transition above and below the critical temperature? Now, I don't mind if we
I can take
have an
it
answer for that
if you want.
Good. Okay, Gabriele?
Yes, I think he's referring to CO2 because, to my knowledge, that's probably the tricky fluid that goes in different phases. Hydrogen, it will be gas, and maybe there are other couple of fluid. Anyway, it depends on the composition. First of all, composition is very important. But if you transition from gas to liquid, definitely will go through a two-phase region. So the answer is it will not be homogeneous in that transition region. And how big or small is the transition region depends on the composition and obviously on the temperature and pressure condition. If you are working well above the two-phase curve or below, depending if you want to stay in liquid or gas, I'm referring to CO2, you need to stay well away from these boundaries, two-phase boundary, if you can. In that case, then you will have a single phase. Yes.
Okay.
So that's the answer, at least for CO2.
Sure. Well, I want to say thanks to Mark for answering that question, asking that question, and I'm sure, Mark, if you want to get in touch after the event, please feel free to. Because of the lack of time, folks, I'm going to go on to the very last question, simply because this really appealed to me. This question when it came in. What is your favourite flow meter? And what developments do you envisage coming to this technology? Manus, I'll ask you to go first because you've already told us you're a Coriolis guy.
Yeah, sorry, I'm Coriolis through and through. Direct mass flow. There's no substitute for that. High precision, low uncertainty, immunity to flow profile effects, readily dealing with messy fluids, and now we can do multi-phase, which is great. And all right, the disadvantages of the energy usage, the cost, pressure drop. What's new? Vibrating in two or more modes simultaneously, and we're actively developing here. And what's great is you get a mass flow and a density reading from each mode of vibration. So you can use that for conventional diagnostics or getting, it's particularly interesting in multi-phase where you get different errors on the different modes of vibration, and that can lead to improved corrections. But I think the real sort of potential benefit of multi-mode operation is that you end up with relaxing the design constraints on the flow tube itself. So, and again, without going into all the detail, improved cheap transmitter electronics and signal processing can then be used to drive flow tubes that are lower cost or made of different materials or lower pressure drop for a given duty. And that's all because we can actively track and compensate for the frequencies of two or more modes of vibration simultaneously. And we're working really hard on this right now. It's looking really good.
Thank you, Manus. Piotr, you had your hand up straight away. You obviously have a favourite flow meter.
Yes, well, I think that the question is wrongly formulated. It should be formulated, what is your favorite flow meter and why is it a turbine meter? No, that was a joke, of course. I'm actually, well, the thing is that depends on the money you have. Ideally, if you have a lot of money, the Coriolis should be quite a good choice because it covers all the type of liquids, provides you enormous amount of information if you can, of course, process it. But then again, yeah, it's up to your application. So I like Coriolis meter, but on the other hand, if I have like a pure water, turbine's fine. Could be orifice plate, anything, basically.
Okay. Gabriele, do you have a favorite?
Well, my background is fluid dynamics. So I tend to, at least in the past, to go towards meters that have a more fluid dynamics, let's say, focus. So I definitely come from Venturi tubes. But as I was chatting the other day with Chris, since a couple of years, I start to spread my love to other technologies. And I can see the beauties of each technology, and I think each technology really is really great and has its beauty. Coriolis, of course, as we said, but also ultrasonic, all what is behind the speed of sound, transducer, and that's fascinating, really. Turbine, it's a very good device. We can see for gaseous that is very, you can predict with the PTB model, you can predict their output and in terms of Reynolds number and so on. And, you can apply to hydrogen, you can apply to CO2, you can apply to nitrogen. So, I think each meters is really on, strength and beauty. And I pass to Chris. And I know what Chris is going to say.
Yeah, but my view is quite similar to Manus. But there is pros and cons to all meters. I think that's key, as Gabriele, Piotr, and Manus have said. But I have a lot of experience with Coriolis meters. There's a lot of advantages. There are some disadvantages as well. But I think going forward, one of the key things, certainly with regards to the energy transition, maybe not touched upon too much, is calibration transferability. So calibrating in one fluid and then operating in another. And that's one of the key benefits of Coriolis meters. You can buy a Coriolis meter and it can be applied to single phase gas or single phase liquid. And as Manus said, there's the developments now for 2-phase, even 3-phase flow with Coriolis devices. But interestingly, there's the potential to calibrate them in readily available fluids such as water or nitrogen gas, for example, or air, and then apply them to more challenging fluids. So I certainly think Coriolis meters, again, are going to have a bright future going forward. I think Gabriele had a point to touch upon there.
Last things, Colin. I know we are... for Coriolis meter, you don't even have to calibrate them. I know you can apply it to different fluids. That's my closing point. But for orifice.
I'm going to bring things to a close here, folks. I've got a few things to say. I would just like to point out, as I did at the start, that we are being sponsored today by DSIT and not by the world's major international Coriolis meter manufacturers. Although I'm betting...
I think that's very unlikely.
I'll come back to you at the end, gents. I just want to point out a couple of things before I say my final goodbyes. I want to let you know a little bit about TÜV Süd. For those of you who are not sure, we are a testing, inspection and certification company. We have over 15,000 experts in over 1,000 countries and over 150 years of experience in safety, security and sustainability. We here at East Kilbride, as has been mentioned, are the UK's designated institute for flow measurement. This is a picture of our water and advanced multi-phase facilities. Interestingly for me, when I give people tours of the facility, they're quite surprised that we use things like PD meters. I think they expect we'll have million path ultrasonic meters and Coriolis meters with tubes that extend into the fourth dimension, but we don't. We use PD meters, we use turbine meters, and because we have that confidence. So that today for me has been a very interesting to hear the opinions of 4 extremely knowledgeable metrology professors and doctors on the traditional technologies. At NEL here, I just want to let you know that we can support all areas of the energy industry, including flow and non-flow related services. meter testing, calibration, virtual flow metering, computational fluid dynamics. We're doing a lot now with hydrogen certification and, as you heard, carbon dioxide flow metering. And then I also want to let everyone know, primarily because I'm the chair this year and I want lots of people to turn up. In October in Aberdeen, we have the Global Flow Measurement Workshop. This will be the 42nd year of the Global Flow Measurement Workshop, one of the world's foremost flow measurement events. This year we'll have a lot of oil and gas, as well as a lot on digital development, CCUS and hydrogen. I'm hoping that everyone on the panel will be there. I'm running out of time, folks, so if you just want to go to our website and you can sign up to our mailing list, and we'd love to see you at the event in October. We do have 4 events in June: the EIC Energy Exports in Aberdeen, the Global Offshore Wind in Manchester, Scotland's Supply Chain Exhibition in Falkirk, and the 3rd of this year's measurement focus group meetings is in Aberdeen. The 4th one will be in London later on in the year. It's 1500 exactly. I just want to say a huge thank you to Chris and Piotr and Gabriele and Manus. I personally have learned a great deal from today and I've really enjoyed moderating it. And I want to also say thanks to Richard and Amelia and Sarah for bringing it all together and advertising it. So I think I'm just going to say goodbye. Thanks to everyone for attending. Thanks to the panelists for giving up their time and you know, their fantastic answers to all the questions. If there are any other questions that we haven't got round to, we will get back in touch with the sender individually and answer their questions. So with that, everyone, I'm just going to call a close and say thank you and goodbye.